Welcome back. So let's go to the joins then. How do we do joins with SQL? Well, there's multiple ways. So I'm going to show you the different ways that you can do it. The first way to do it actually doesn't require any additional clause of keywords. It just requires a comma in the from clause. So if you look closely what is happening here, so you have these two tables on the left and on the right, so a table of persons, a table of spaceships, and you might have noticed that the spaceships have a captain, of course, which is here. And so I want to join the captain of the spaceship together with the name of the person. This is what I want to do. How do I do it? Well, you might remember, so this is a theta join because it's not the same column names, so it requires a predicate. It's not a natural join. Do you remember that the theta join is basically made of the composition of two algebra operators? Do you remember which ones? Can you decompose the theta join into two algebraic operations? On Zoom, maybe? Does anybody on Zoom know? Nobody knows? You don't remember? Does Cartesian product ring a bell? Remember the difference between a join and a Cartesian product? That in a Cartesian product, we look at all combinations. In the join, we only look at the combinations that matched. So a join is basically a Cartesian product followed by a selection, exactly. And the selection has the predicate of the theta join. So this is how you can do it. You basically do it explicitly as a Cartesian product and a selection. How do you do the Cartesian product in SQL? It's as easy as a comma. You just put two tables here, comma separated, that's going to compute the Cartesian product. So if you just say from person spaceships and you forget about what's down there, just from person spaceships, that would be the Cartesian product. It would compute all of the combinations. But you need to also have that predicate for the theta join, so that would be the selection. How do you do a selection in SQL? With what clause? Where, exactly, that's the selection with the where clause, and that is your theta join predicates. That would be the subscript of the theta join. And the predicate says the person's last name here must be the same as the starship's captain name. So does everybody see we have the Cartesian product with a selection to make the tuples match? Who sees that? Okay, awesome. So this is the first way you can do it. This is the first way that you can ask for a join. And then we only select, at the end, we project to the century and warp, so we get these two. So do you see how we obtain that? Basically, Kirk goes with these two. Crusher is not a captain. Picard goes with this. Janeway with this. So we basically have 1, 2, 3, 4 matches in the join. And for every one of these matches, we are going to return the century and the warp. So this first match gives you century 23, warp 5. The second match gives you century 23, warp 4. It was a different generation of the Enterprise spaceship. Then we have 24, that's the third match with Picard. Picard, that's the next century. So warp is getting closer to 10, 9.2. And then Janeway, that's even later, the warp is 9.975. There's even an episode in which there's a warp of 10, and then they go back to the origin of the universe somehow. But anyway, this is what you get. Cartesian product, followed by selection, followed here by a projection. We don't have to, but this is what we did. For whom is that clear? Okay. So this is the first way you can do a join. This is the second way you can do a join. You can also explicitly use the keyword join. It's not a clause. So it's not like select from where, group by having. So join is not in that list. Join is really something different. Join goes inside the from clause. So we really have that from clause in here. And in the from clause, we have persons join spaceships. That's together in the from clause. And where do you put your predicate? You use the keyword on. So we say persons join spaceships on person's last name, spaceship's captain name. That's the subscript of your theta join. Who understands that? All right. This is the same thing. This does exactly the same thing. Now you might wonder, does it make any difference with performance, right? Because you might think this is faster because here it's a join and you tell it's a join. And here you might think, okay, there's a Cartesian product in there. Imagine you have a table with 1 million records on the left and 1 million records on the right. If you want to match them one by one, it might be the output only has, let's say, 2 million records, right? But if in between you do a Cartesian product of 1 million and 1 million before the selection, you will end up with 1 trillion records in that intermediate table. Who sees that? Right? So the Cartesian product would give you a gigantic table. So you might think this is inefficient. And if you try to join 2 tables with 1 million records, that's going to crash your machine. It might be surprising, but it is not going to crash your machine. You can actually do it. Like virtually, you're going to have an intermediate results with 1 trillion records. And what's incredible is that you can even do that on a small laptop, not so much memory and not so much CPU, and it will just work. The reason has to do with the power of optimizations and how smart PostgreSQL was written. Because what happens is that PostgreSQL here is going to figure out the Greek letters. So it's going to figure out that this is a Cartesian product, then a selection, then a projection. But PostgreSQL will look at that query plan and try to figure out what it can optimize. And PostgreSQL will see that there's a Cartesian product followed by a selection. So it will think, that looks like a join. And it will replace in that query plan this Cartesian product and selection with a theta join. And the theta join, it knows how to optimize. There are ways we can use what's called the hash table and so on when the predicate is an equality. So we can actually do it quite quickly. So what's very important to understand is that what you write in your Jupyter notebook, even if it's inefficient, often, not always, but often, PostgreSQL is able to be smart enough to figure it out and make it faster. So this is an example of it. Even though you do have a Cartesian product, PostgreSQL is smarter than that, and it will be able to circumvent that all by implementing that efficiently. That is one of the benefits of using a functional language, query language like that, over Python or Java or some other language. Because in Python, it would literally do what you ask it to do. You do have, of course, a few compiler optimizations, but they cannot go as far as the sort of optimizations you have in SQL. And doing that sort of things is really, really where lies the power of a language like SQL, that it's magically fast, even if you write without thinking too much about it. For whom is that clear? Okay, so this is the reason why, even though it looks like this would have 1 trillion records in the middle, and here it's directly a join, in fact, it will be exactly the same and take roughly the same time to execute, right? Because the query plan, it will basically transform this into this in the query plan. Okay. This here, what you see here is really all in the from clause. So it's not like there's a select clause and a from clause and a join clause. No, no, no. There's really a from clause, and inside the from clause, there is this join thing. This is called a table expression, what you can have in there. So we see there's several kinds of them, but this is one example. The simplest table expression, of course, is just the name of one table, which we've been doing already for an hour, even 1 hour last week. But this is a more complex table expression that involves 2 tables, joins them. The comma is also, that's also a table expression, persons, comma, spaceships. That's basically the cross products, the Cartesian products. So this is another table expression. All right. Here's another table expression. In fact, this here is the verbose version of the comma. If you don't like the comma, you can just write cross join instead of the comma. So for example, you could replace here persons, comma, spaceships with persons cross join spaceships. It's a bit weird to call it like that, but cross join is basically the Cartesian product. This is called cross join by, yeah. So this is a Cartesian product. Now, there's no where clause in there. That's how you crash your machine. Do not do it at the exam. Some people do it at the exam, they are not careful, then it crashes the machine, we have to move them to another one. Be very careful, do not do that. This is how you crash your laptop. You can try it now during the semester, take your laptop, do it, crash it, restart it. You will see how it basically goes. Of course, here it's not going to crash because there's 2 and 3, so there's 6. So here it's okay. But if you have persons with 1 million entries and spaceships with 1 million entries and you say cross-join, this is going to crash your computer. It might be that it only crashes Jupyter and it suffices to restart Jupyter. There's a trick, by the way, at the exam, if that happens to you, if you notice that it's only Jupyter that is no longer answering, but the rest of the computer works, in the menu, you can go somewhere and say restart kernel, basically, like close everything, restart kernel. Then it's just restarting the whole thing, and then it works again. And then you don't need to be seated somewhere else. But if somebody really pushes it and does something actually huge, that it doesn't only crash Jupyter, but even the laptop, then the computer, then we have to find another computer. Okay, so I think I have talked about it long enough that you know that you should be scared of that and be very careful about that. Avoid a Cartesian product if you don't have a where clause to specify a join. Okay, in fact, they are so dangerous that when you have technologies like, have you heard of Spark, Apache Spark? Right, that's a technology that's basically taking this to the next level on clusters of machines in a data center. The Cartesian product is so scary that by default, Apache Spark is configured to refuse to do Cartesian products. By default, if you try a Cartesian product, it will tell you, no, sorry, I can't do that, Dave. Right? So you really have to activate it. So, all right. I think I've made the points. These two are equivalent. Okay. Here's another one. That's called an inner join. Well, in fact, it's the same. If you just say join, by definition, it's an inner join. I've never said the word inner. I said the word outer, I think, outer join. I explained 2 weeks ago, but I didn't say the word inner join. Well, inner is just when it's not outer. It's the opposite of outer. So typically, if you don't say anything, if you just say join, it's going to be an inner join. What does it mean, inner join? It means that the values that don't have any match, you might have values on the left or on the right that are orphans. They don't have any match on the other side. In an inner join, you just don't include them in the results. That's what an inner join is going to be. Concretely here, it means that, Crusher. So Crusher here is not in any spaceship, not the captain of any spaceship. As a consequence, because it's an inner join, she will not be included here in the results, right? You don't see Crusher here. For whom is that clear? All right. So again, it's the default. So if you just say join, then this is an inner join. Right? Now, okay, so this is the one. Now you can say that you want an outer join in the sense that anything on the left that doesn't have any match, you put it in the results nevertheless, like here. And you just put nulls because there's no match on the other side. You don't have anything, just fill it with nulls, right? That is an outer join, but more precisely, it's a left outer join. Why left? Because here we say it's only for the match, the values on the left that don't have any match that we do that, right? So this is why it's called a left outer join. Now, imagine just for the sake of the example, I'm removing Picard from the list of persons. So let me remove Picard. Now, Picard in the spaceships, that tuple doesn't have any match anymore. So what you can do is a right outer join in that case. If you do a right outer join, it means the tuples on the right table that don't have any match, you include them in the results and you fill the left part with nulls. Who is with me? Right? Yes? Yes, so the question, let me reformulate the question for the people on Zoom. You're basically asking what happens if the table persons was created with a create table that says that first name, middle name, last name, century captain is not null. You basically had a not, that's what you're asking, right? And now you see these nulls over there. Well, the idea is that the table that you see at the bottom, that's a table that doesn't, it's not persisted, right? It's something you create on the fly. So this is why it's not a problem that we have this null, because when you say not null, that's a constraint on persons, the persisted table. I think that you wouldn't get an error because so it would put the nulls, I think. That's what I would assume. Maybe you can test if you have a moment, Xiaochen. Yeah, does it make sense? So basically the key is really the table at the bottom here is not the same as the table persons. So it doesn't have this, I would assume it doesn't. The reason I assume that is that it would be limiting if you, because then you have a join that fails, that would be very strange for me. But I also put that on the list of the things we will check to make sure that, that I'm correctly telling you that. It's a little bit like when you have average of something that changes the integer into a numeric. That's a bit like that. So basically, when you create tables on the fly like this, then the domains start having their own life. It really does whatever makes sense with them. Okay. And in a way, you're already forcing something here because the default is just join. So here that will not happen, right? So if somebody bothers to actually write outer join, that's really a way of forcing things, right? Of telling PostgreSQL, I really, really want to have these nulls in there. Okay. Does it answer your question? Yep. Under the reserve of checking what I've just said. All right, so this is a left outer join. Take the visual of that. So left outer join means it's the tuples on the left that don't have matches. We fill with nulls on the right. And the right outer join is the tuples on the right that don't have a match. We fill them with nulls. As you might imagine, there's also what's called the full outer join that is both left, right, and center and everywhere, where you just take all the tuples, no matter where they are, and fill with null the other sides. Does it make sense? Okay, that is a full outer join. And now we have the one that is called the natural join, so the one that has the same column names on both sides. So imagine that I did a change here in the data. I changed the name of the column. It was called captain name, and I changed it to last name. See the difference here? So now we have two tables that share a column name. It also has the same domain. That's a good thing. So now we could do a natural join. How do we do a natural join? We just not write natural join, right? Of course, natural is compatible with outer. So you can have a natural inner join, a natural left outer join, a natural right outer join, a natural full outer join, right? So here it's a natural full outer join, and that gives you this. And the difference with the theta join is that you don't need a predicate because the predicate is implicit. It's implicitly telling you the last name must match the last name. Okay? So this is here a natural join. And as a consequence, the column last name only appears once in the output. We don't repeat it. Okay. Great. And as I said, it's orthogonal to inner join. So you have the full outer join, the natural inner join, and so on. So here, of course, I believe it's a typo. Is it a typo?
For the person's name now, but not the person's last name.
Oh, yes, that's a leftover. I thought I had fixed it. Where is that? Person, yes, person's.name. Can you maybe please make a note? I'll fix it. You're absolutely correct. I forgot to change it in here. It should be persons.lastname. Yeah. Thank you. Slides 150 to 154. We'll fix it. Okay, thank you for that. Thank you for noticing. It means you understand. So that's great. Okay. Oh, yes. So here, I didn't just change to inner join. That would actually work here. You could do an inner join. You would just not have the two lines with nulls would not be there in an inner join. But here I did something else. I also changed the names of the columns here and here. They used to be called century and code of the spaceship. And now I changed them just for the purpose of showing you something to the same name. So now that is an example of an accidental coincidence of column names, right? For last name, it was intentional. It was the intent that they're supposed to be joined together. But here, that would be something accidental. It means that it just happens to be that these two tables use the same column name, but in fact, these columns have nothing to do with each other. On the left, C is a century, and on the right, C is a spaceship code. So What is the deliverable here? Well, if you try to join them, of course, you won't get anything because the spaceship code never matches the sentry. But the even simpler answer is you should not do this. You really need to pay attention. If you try a natural join, you really, really need to double check that the column names are really what you intend. Always double check that you don't have accidental equal column names and you just don't notice. This is how you avoid issues. And actually, I think it happens in the exam data set. You do have some column names like this, and you have to be careful. But the conclusion is easy, just avoid the natural join. If you're in doubt, don't do a natural join, just write the predicate explicitly like here. Then you're safe. Here you know that this is exactly going to be matched like this. Okay, so this is my word of warning, right? Double check that you don't have column names that are the same by accident. All right. By the way, if that happens and you want to avoid such an unintentional match of columns, there is something simpler than the predicate. Remember that the predicate is with on, right? So you have a full outer join on, and on is followed by the predicate. But now imagine that you want to be very careful, like you notice that you could have unintentionally equal columns, but you don't want to write the whole on persons.last name equals spaceships.last name because it's the same column name, right? So this is something in between. It's the same column name, you know it, but you're a bit scared of doing a natural join because you don't know what the other columns are. But you're also lazy because you don't want to write the whole on clause and equality. That's okay because the using clause comes to the rescue. And the using clause does exactly that. It's basically a theta join, but it's a theta join that specifies the column names that are equal and that you want to include. So in that case, it's safer than a natural join because here you match last name with last name, and you don't need to check if there's other column names that collide. For whom is that clear? Okay. So again, if you don't say anything and it's natural, use with a lot of care and double checks. You can use using if it's the same column name and you really want to specify to only join on this. And the most general case is with this on clause that specifies a predicate. In fact, the on clause is so general that it doesn't even need to be an equality. It could be anything in there. You could do an on with a greater than, a smaller than, and so on. Of course, it's going to be bigger, but it doesn't need to be an equality. If it is an equality, it's going to be very fast because the joins with equality predicate that we know how to make them fast with PostgreSQL. Okay, so that's the using clause, and the using clause would basically give you exactly that. That's another example here where you would have name and name. So here you basically would be tempted to do a natural join because you see last name and last name. But now you notice that's a problem because the name of the person that has nothing to do with the name of a spaceship. That is a typical case of using the using keyword. Now you say full outer join spaceships using last name. Now you're guaranteed that the name and name are not going to interfere. So this is going to be fine, right? However, you have a problem because in the model, we said the columns must be unique, right? So now we kind of have some outputs because we didn't join the match on these two columns. So now they have the same name. So what happens is two things. So first, if you're in the math, you should rename them. So it means that you should first specify a different name, let's say P name and S name. How do you do that? When you disambiguate the name with the name of the table before. The table.name, and then you can rename them as P name and S name. And now you're safe, right? You see P name, S name. So that's how you do it. So the new thing in there is really this dot here, the table dot a column name. Technically, you can always do that. You can always say the table name, the one here, dot name, but it's not needed. It's only needed if you have a collision, if you have two columns with the same name. Okay, happens all the time in practice. So this is really very useful to be able to disambiguate which column you mean. Do you mean this one or do you mean this one? And you just add the name of the table in front. Who is following? All right. By the way, you can also specify an alias. If you're too lazy, computer scientists are very lazy. So if we don't want to have to write it in full, because you would have a large query where you have a lot of ambiguities, you can specify an alias here for the table, persons P, spaceships S. And now instead of persons, you can just write P. Instead of spaceships, you can just write S. That's an alias, right? There is no as in there. In that case, it depends a bit on the engine, but you just say with a space in between. It's not like persons as P, but just persons P. All right, and that's what you get out of this. Everybody with me? I keep introducing new things in there, right? Okay. Now, I'm going to talk about self-joins, joining a table with itself. When does that make sense? Well, for example, with genealogy, imagine that you're studying your ancestry and you have a whole table with people, and then you have a parent relationship, that some people are the children of some other people. And let's say you want to study like the grandchildren or the grandparents or the great-grandparents. So it means you need to have joins multiple times and with the same table, right? So that's called the self-join. So here I didn't do it with genealogy, but I did it with the genealogy of spaceships. So basically, every spaceship had a code, but it also has a successor. So the successor of A is B, the successor of B is C, the successor of C is D, the successor of the original right is A, and the successor of D is E, right? So this here is the successor. Do you remember primary keys, foreign keys? Right? So that would be kind of the primary key of that table. And that would be a foreign key. Remember, references? But the difference with before is that this foreign key here is actually pointing to the same table. And that is absolutely possible. And again, think of a table of people and you have parents, and then parent points to another person in the same table. So this is a foreign key that references the primary key of the same table. Right? For whom is that clear? All right. So technically, we very often do joins based on a foreign key and a primary key, right? The join predicates is based on the foreign key matching the primary key. So I'm done talking? No, I'm not done talking. What's going on? Did I mute? Zoom is saying that I'm done talking. Just checking. Can you hear me on Zoom? Yep, awesome. So it's just Zoom acting up. Okay. So I'm going to do a self-join. In fact, it doesn't change the way compared to before. The only thing that makes it a self-join is that now I have the same table on both sides, right? Spaceships join spaceships. That's what makes it a self-join. But in order to disambiguate, I do it with aliases. This one, I put an alias of S1, and this one, I put an alias of S2, right? So I join a table with itself, but S1 is going to refer to the one on the left, and S2 is going to refer to the one on the right, okay? Then I have my predicate. I'm basically saying that the code of the second one, the successor, must match the successor of the first one. And here, again, this S1 and this S2 is the way that I can tell them apart, even though they're the same table, but there's really one on the left and one on the right. And then again, I use this S1 and this S2. S1 is the former one, and the other is the next, and I get this. Who understands this query? Okay. Yes? Oh, sorry, I thought you had a question. Oh, yeah, because I asked who understands this query. Now I realize. Thank you. So you see now it's organized because I use the names now. So enterprise, the successor is enterprise A. The successor of enterprise A is enterprise B, and so on. All right, so everything is in order. And basically, what we joined is like this, and that's it. These are the four matches. Okay. Now, it sounds complex, right? Cross join, inner join, left outer join, right outer join, full outer join, natural inner join, natural, there's probably even natural left outer join, natural left inner join, natural full outer join. So there's a lot of possible combinations. So what you need to know is first, if it's just a comma, that's a cross join, that's the Cartesian product. If you just say join, then it's always inner by default. If you say left join, then it's always outer. A left join is always a left outer join. So you can also just right left join. Right join is always right outer join, and full join is always full outer join. So what's in gray here is just what you can omit. That's your intent. Okay. An opportunity to ask any questions. I'm done with the joins now. Any questions? Anything? I see no. So everybody understands then. Awesome. And now I see people nodding. All right. So let me recap what we've done. We've looked at the clauses. Remember, select, from, where, group by, having, order by, limit, offset. Then we looked at table expressions. That's what's in the from clause. In the from clause, you can have a single table or you can have multiple tables. And when you have multiple tables, what you can do is you can combine them with a Cartesian product, also called cross join, or just a comma, or join, inner join, outer join, left outer join, right outer join, full outer join, natural inner join, natural outer, and so on and so on. So all these possibilities. You can put aliases for the table names. If you're too lazy to write the name entirely, you can give it an alias. The aliases are especially convenient when you have the same table joined with itself. Then you need the aliases to disambiguate the site. And you also need the using clause if you want to do something that looks like a natural join, but you want to be in control of the columns that you match. So now that we've done that, let's move over to the set. You remember union, subtraction, intersection. So this is what you can do in the algebra. So this is, for example, the union of two tables. How do we do it with SQL? As you might guess, with the keyword union. And this is how it's done. You have basically a select from where, group by having, order by, limit offset query on the left, then union, and then another select from where, group by having, order by, limit offset, and so on the right. What you need to remember is that what you need on both sides is really the whole select from where thing on the left and the whole select from where thing on the right. You cannot do something like select star from spaceships, union spaceships too. That doesn't work. You cannot just union between two table names because union is not a table expression like the join. It's really an operator that takes a whole select query on the left and a whole select query on the right. Okay? And that gives you this table here. Now you might notice I have 3 tuples in spaceships 1, 3 tuples in spaceships 2. That should give me 6, but I can only see 5 here. Why is that? There is a duplicate. Can you see the duplicate? C, exactly, enterprise C. So there is a duplicate. And indeed, when you write this union in PostgreSQL, PostgreSQL eliminates the duplicates. If you don't like that, that's okay. Oh, I don't have it here. Where is it? Yes, here. If you don't like the duplicate elimination and you really do not want to eliminate duplicate, just write union all. If you write union all, then you deactivate the duplicate elimination. So here you would have a duplicate. Note that you are in the bag of records. That's bag semantics if you do that, because you have duplicates. All right, and you can do it, by the way, not just with union, but also with intersect for the intersection. Intersect, just like union, needs the whole select from where, group by having, order by limit offset on the left, and the same thing on the right. We get that. And except, that is the subtraction. It's spaceships 1 minus, or more exactly, set minus spaceships 2. That is all the tuples that appear on the first table, but without those that appear on the right. So since the intersection is C, then C goes away, right? You just have A and B, and C is eliminated. Just like you can have union all, you can also have intersect all and subtract all, right? In the same way. Who is with me? Okay, so here it's really easy to learn. You just need to remember union, intersect, and except. That was actually quick, right? That's all there is to say about the set operations. So again, the one thing to remember, because this is really a common mistake, a lot of people are tempted to write union, intersect, or except inside the from clause with two table names, but it really doesn't work. You need the whole select on both sides. So now I've pretty much covered most of what there is to be said in the select from where clauses and in table expressions and in set operators. So I can now move on to something that is a bit more advanced in SQL, which is the concept of nested queries. So this is where the serious stuff begins, and you get into full professional advanced mode with SQL queries. What do I mean with a nested query? Probably have some example. No, let me just tell you. It's not, the slide is not right now. A nested query basically means that you have a select from where inside of another select from where, inside of another select from where, just like the Inception movie, a dream in a dream in a dream in a dream. So this is called a nested query. So this is really when you start compounding your query because it's a functional language and you have a query in a query in a query. So I'm going to explain it to you and try to make it understandable. So when you nest, first, it's very important to understand what you nest, or at least what kind of data is flowing when you nest the queries. So you need to understand that when you write a SQL query, there's really two kinds of things that flow in these queries. The first kind of things that you have is tables, entire table. So when you have a select from where, that produces an entire table, right? On the one hand, so the tables. On the other hand, you have the scalars. When do you have the scalars? Well, when you are in the where clause, for example, when you say foo is equal to bar or foo is greater than or equal to bar, you're manipulating single values, right, on every record. These are called scalars. For example, the string, null, true, 6, pi, some date, and so on. These are all scalars. So you really need to understand in your mind that there's these two kinds of things. There are the tables and there are the scalars. If you're familiar with linear algebra, the same thing kind of happens in vector spaces. You have the vectors and you have the scalars, right? So a vector space is built on a field, and then the members of the field are the scalars in the vector space, as opposed to the vectors. For whom does that make sense? And if you don't know linear algebra, that's okay. That was just something that I said in case you're familiar with it. Okay, so tables and scalars. So now it's very important that you understand when you write your SQL query, when you write something, you really need to be clear in your mind, I am manipulating tables or I am manipulating individual values, atomic values, scalars. It's very important. Because when you say select from where, having, or even join, and so on, you're manipulating tables. But when you use things like plus or greater than or equal or and or sign, or that's a trigonometric function, or 3.14 and so on, you're manipulating single values. For whom is that clear, the difference of what you're manipulating? See, raise hands just to make sure. Okay, very good. Okay, so these are called table expressions. Well, technically, what you have in the from clause, for example, the join and so on, but even the select from where would manipulate tables, and then value expressions that manipulate single values. Typically, this is what you see in the where clause, these sort of things. Now, what about nesting queries in queries in queries in queries in queries? Well, there's four possible things, four possible ways to do that. You could be nesting an expression that manipulates scalars into an expression that manipulates scalars. For example, 2 times 3 plus 4. 2 times 3 is then nested inside the plus 4. Or you could nest an expression that manipulates scalars inside an expression that manipulates tables. Or you could nest an expression that manipulates tables inside an expression that manipulates scalars. Or you could put an expression that manipulates tables inside an expression that manipulates tables. Right. So I'm going to go one by one, all these cases, and I'm just going to show you what it looks like when we do these things. Okay. So first, this is the easiest, right? So value into value, so scalars into scalars. That's really the math you've been doing since primary school, right? When you write multiplication, addition, and so on, you're basically manipulating single values. So this, for example, 2 plus cast 3 concatenate 4 as big int. 3 concatenates 4 gives you 3, 4, the string 3, 4. You cast it as an int, you get 34, and 2 plus 34 is 36, right? So this is a value in a value in a value, and that's something you can calculate, and you get the value 36 out of this. For whom is that clear? That's the easy part. That's where you can do that in the where clause, for example. That's the basics of calculation. Okay, so that takes care of the first one here, value into value. Now let's see value into tables. Well, in fact, that's something we've already done, right? Because whenever you have a where clause that manipulates scalars, it's in the where clause, so it is inside the table expression, right? So you really see that here, this is a value expression. It manipulates individual values. In fact, these are also value expressions. You remember what this is called? Well, in the projection, we do some computations. This is called an extended projection, right? So in the projection, you can either just project 2 columns or rename columns, but you could also create new columns that you compute out of other columns. So what this does is that it takes the content of column name and it concatenates it with a dot, for example. That's creating a new column, computing on the fly. Or here you would be creating a new column that takes the value in column H, but you add 20 to every value. So that's an extended projection. And that's also a case where you have here a value expression that could contain plus, multiple, and so on, and here another, and here another. And that is an example of value expressions that are nested inside expressions that manipulate tables, like select from where. From whom is that clear? So this is not new. This we've already seen that we can nest value expressions inside select from where. Now, I'm just going to be careful to not finish exactly on the ring. Let me see how far I can go and still having time to ask you if you followed. That I can show. So when you have scalars, let's say I have foo bar 1 and 2, and I would like to build a table and put these 4 values inside my table. You see foo 1 bar 2, so I want to build that table. You can do it like this. This is also SQL. In SQL, you write values foo 1 bar 2 that is creating a table that looks like the one you see here. PostgreSQL is just inventing column names. It's going to call them column 1, column 2, doesn't matter, right? And it also infers the domains. Like it sees that foo and bar is text, 1 and 2 are values, so it calls it big ints. In fact, we've seen that already somewhere. Do you remember the insert into? We've seen insert into. Well, values was in there. We had insert into values, blah, blah, blah. So we've already seen that. But it turns out that you don't need to have it inside insert into. It can be on its own. You can just write on its own value foo 1 bar 2. Try it in Jupyter Notebook. You can write that in Jupyter Notebook. That will give you that table. So this is where I'm going to stop. And this is also the second example where you have individual values, scalars, and you create a table out of that. All right. Which is now the moment, of course, the demo effect. There is your opportunity to control me. Do you want me to accelerate? Do you want me to slow down? Is it too easy? Is it too complicated? So just to get a bit of a feeling. Okay, so we still have a majority above 80%. Do not be worried if you're less than 80% or if you're less than half, do not be worried because I have a secret for you. Use the exercises, use Jupyter notebooks, and write all the queries you can in there. This is how you learn. Do it, write queries, as many as you can, play with it, try things in the Jupyter notebooks. It's fully interactive, you see it live. This is really, really the best way to learn, and you're going to have practical exercises. And the second way is ask questions. So those who are below 80 or less than half, ask questions on the Moodle forum, write me emails, write the TA's email. We are here for you. We will answer your questions. And of course, you should read the book on the databases, right? So that tells me I shouldn't accelerate. And maybe next time I can also start with questions to make sure that, that you're with me. All right, so thank you very much, everybody. Have a nice weekend. Enjoy the exercise session and see you next week at 10 a.m.